morning. It's great to be here. Thanks to the organizers for inviting me to this event, and thanks to all of you for showing up promptly after a festive night. I've been working in the realm of scattering amplitudes in a rather traditional sense, sort of in the context of relativistic particle scattering. So I'll talk a bit about my point of view, and what I mean by constructing amplitudes is finding ways to compute them that bypass the complexity of direct integration of the loop integrals. So the idea of bypassing this has been popular and implemented at several levels over the decades, and the common element is to find what I'm calling a construction here from some kind of ansatz or basis. And it depends then on understanding how to construct such an ansatz or basis to pinpoint the amplitude, eventually the numbers for the cross-section that you're going to need if we're talking about particle scattering. So some examples of this are, let's start with classic unitarity methods. So unitarity is a very big keyword, and that comes from the unitarity of the scattering matrix itself, related to the well-known optical theorem, which implies a relation to cuts, meaning an operation on the diagrams where some of the virtual lines are put on shell. This led to variations of this, which were more powerful. So besides taking some on-shell constraints that are directly related to the unitarity of the S matrix, what happens if you start putting more of the legs on shell? So this is called generalized unitarity, not really generalizing unitarity itself, but generalizing the on-shell condition. So these are called on-shell methods very broadly, and this allows you to put down more classes of constraints on your original ansatz or basis. Some modern terminology that comes attached to the same idea is now the symbol bootstrap. So bootstrap also, right, this general idea of constraining some kind of ansatz, and the symbol is going to be particular to Feynman integrals. This is different from the symbol we heard about yesterday. I'm coming to that shortly. So the key message that I want to convey this morning is that this all comes down to controlling the space of functions. And when I started in this field, then I would give talks, and usually some older members of the audience would say, yes, are you working on or coming back to the analytic S matrix, the old program from the 60s, in which it was hoped that everything would be understood just from analytic properties of the scattering matrix, including unitarity. And that's not wrong. We have been in the business of rediscovering, reinterpreting many of the old ideas, and we've made good use of this classic book. I just excerpted one figure chosen fairly at random to illustrate that it's full of the discussion of analytic properties. So you're looking about curves and sheets and really high-level complex analysis. And okay, so analytic properties provide enormous constraints, but on what functions? And I think this is the big difference between the program of the 60s and what we're able to do now. For example, they'd consider a simple, simple 3-point, don't want to move this thing, there. 3-point function, the scalar triangle integral. And so the diagram I've taken here, figure from the book, has to do with some singularities, following singularities of such an integral onto different sheets. And again, this is not entirely obsolete. It's still, if you write down a formula, we still have to understand how to analytically continue it to different kinematic regions of interest. But my point is that the people working on the analytic S matrix, they never wrote down a formula such as this with all the logarithms that make it so useful. And yes, it's these logarithms that have this analytic structure we see on the left, or an enclosed form hypergeometric functions such as this. So there are a couple elements here. One is that in the analytic S matrix program, everything was completely generic and they would talk about being in different dimensions, but it was understood it would be integer dimensions. So one big difference is now we understand it's very convenient to work in dimensional regularization because masses are also not generic. In real life, we need to deal with a lot of massless particles. That's what we get in high energy collisions. So therefore, what I've highlighted here, this is a specific example which would not really have been considered. The fact that, so I'm just using the heavier lines to indicate massive particles. So here's an internal mass, and here's one with p squared non-zero. The others are massless. So, okay, so there's just a p squared and an m squared in this expression, which are the p squared and m squared, of which this is a function. So this is a bit more particular. If you really had generic masses, there would be a function in terms of hypergeometrics and polylogarithms. It would be a bit more complicated than this, but we could write it down also. And, okay, working now in dimensional regularization, so this epsilon here, this is the parameter of dimensional regularization. So it's important to be able to pull that down out to do a series expansion and to read off the coefficients. And so, inevitably we encounter ultraviolet and infrared divergences that will be controlled, and we just have to understand how to control them. And I think really crucial to all the success of recent decades has been finding or understanding how logarithms end up in here, and more generally polylogarithms. So the logarithm and the dilogarithm shown in the previous slide, those are examples of polylogarithms, this larger class of iterated integrals defined here. Okay, so now the symbol that we're talking about is a symbol that really goes along with polylogarithms and can be defined for some classes of iterated integrals more generally. So by now there is such a thing as symbols for elliptic integrals as well. So from the form of the iterated integral, there's a way of reading off symbols. And here's just, well, in the faint gray, an example of what a symbol might look like. And symbols are very useful because they encode basically all the relations that we know among logarithms and polylogarithms. For example, this is not quite the famous 5-term identity, but here's an identity involving the dilogarithm. And there are more, and the point is you can have these, especially when you write them in terms of more general z's, you can write down all kinds of relations. But the relations really boil down to if something is going to be equal to 0, so then you can easily collapse it, map it onto something that you can manipulate algebraically in tensor algebra, and find that's 0. So from this relation, you might still conclude, it doesn't follow directly that if a symbol of something is 0, that the thing itself is 0, but if you test some numerical points, you'd find that this indeed is identically 0. And the fact that the symbol is 0 is already telling you that you're pretty close to an identity. This is useful for Feynman integrals because many Feynman integrals are polylogarithmic, all at one loop and many even at higher loop order. Okay, so back to the idea of a construction. So symbols are very useful for construction. On-shell conditions probe the discontinuities at singularities. That's what you are measuring when you evaluate that integral in which you put some things on shell. So this can be interpreted as a discontinuity across a branch cut or an imaginary part of an analytic function. And discontinuities also expose the symbol structure very nicely. So we've said, unitarity methods are finding, the idea of finding coefficients of a basis of some known, what are called master integrals, distinguishing by projection onto cuts. So if you have different sets of edges, which are subsets of the edges of your original graph, then they'll have some on-shell conditions in common. So both discontinuities and differential operators are very very naturally connected to the symbol in this way that I've indicated here. I haven't said yet what delta is. Delta is a coaction, another algebraic operation, which basically corresponds to the symbol once you iterate it as much as you can. What it's saying is that on symbols, if you take a discontinuity on the function, what you get is the same on the symbol as if you take the discontinuity of just the first part of the symbol. And for a differential operator, it's the complementary condition. You only need to differentiate the last part of the symbol to get the result of the differential operator. Now, our current state-of-the-art methods for evaluating multi-loop integrals, there are different kinds. By the way, I'm referring to very large bodies of work here without any references because there are simply too many, but there are throughout the talk. There are some that rely on unitarity methods, which are essentially cuts, and some that rely on differential equations, some that combine both, and so for both of those kinds of operations, it's very helpful to know that they work well with a symbol. This is, I guess, one aspect of it that I personally have been involved in. So if you want to understand what the symbol of a Feynman integral is, I've just shown one example. You might take a coaction of a certain two-loop integral. And with my collaborators, we've outlined, I guess, a proposal that you could do this at the level of diagrams too. That you can evaluate such an integral in terms of polylogarithms, and then you can compute the symbol. And we claim that would be the same as if you do an operation at the level of graphs first, and then expand the symbol. And this can give you some information about how the symbol is put together. That's what I mean by saying physical considerations, meaning the diagrammatic structure constrains the structure of the symbols. And what the graphical operations, so what we've done here is we start with some graph, and in the first part, the part that will still, on which you'll be taking further discontinuities, you get integrals that are related by having the same edges or some subset of internal edges. And in the second part, the part on which differential operators will act, you get naturally cut integrals. That's what these red lines are indicating. Those are the ones that are being put on shelf before you evaluate them. So I've shown a two-loop example to be fancier here. One loop is under more control. So at one loop, in the generic case, you can actually then read off what the symbol would be. So we have, that's coming back to this expression I showed earlier, we have sort of three representations of the same concept. We have a Feynman diagram written as a graph. You can evaluate it in dimensional regularization in terms of a hypergeometric function, or you can expand it as a series expansion in the dimensional regularization parameter, giving the logarithms. And so they give three versions of this coaction, which can be expanded into a symbol for the polylogarithms. And all these coactions, indicated by delta, they all have a common structure, which is, if you represent something as an integral, which is a pairing of an integrand and an integration contour, then you get two items in the tensor algebra, and they're related by changing the differential form and the integration contour in a specific way. So these integrands are related by integration by parts identities, and here you just have to find a set of new contours. What I want to come back to is the idea, we need to understand the space of functions, which might be polylogarithms, but which polylogarithms? It's these ones. This is really what I mean by the space of functions. If you start with your integral, how do you meaningfully expand it by finding the basis, in math terms, a basis of cohomology and homology, to fill out is what you could call elements of the period matrix. This is the space of functions that you want to have control over.
What are the differential forms?
Well, it would start with the integrand of the Feynman integral. It's determined by the propagators for the internal edges. There might be some numerator as well.
And the index I,
Okay, so I'm just summing over I, so there is some basis. So it's that, yeah, for a real Feynman integral, an actual Feynman integral, you would find those in practice by applying integration by parts identities, and it turns out that this, the space will just close. They do have some finite dimension, and now we understand what the dimension should be. Okay, so that was the more general part. Now in the final portion of the talk, I want to come to the way in which I've been exploring the function space of Feynman integrals more recently. I've been looking at a way to actually change these integration contours by studying the on-shell conditions without momentum. So what actually I should come back to, this formula here, where we change the integrands and the contours, this really corresponds very clearly to what we're doing here. What you get by integration by parts relations are the first entries in which you've changed the set of propagators. I'm sort of sweeping the numerators under the rug. They can come along for the ride. And the second part, where you change the integration contours, that's really when you put things on shell, you can interpret that as taking residues, if you like, or in some way changing the integration contour of the original integral. So it's really just that. Okay, so I've been looking at, so one way of presenting a Feynman integral, you can do them directly in momentum space. You can also use Feynman parameters. So this is a representation in terms of Feynman parameters, where we have the well-known semantic polynomials, graph polynomials that you read off from the parameters. You have one for each edge. Of these two polynomials, all your kinematic dependence is in one of the polynomials, which is the F polynomial. And if we're looking for discontinuities, we're interested in discontinuities as we vary the kinematic parameters. So we're really focusing on F. Here, this integration domain, as we set up, use the Schwinger trick to introduce Feynman parameters, is given by having all the alphas non-negative. So the boundaries of the integration region are alpha I equals 0 for each I. So my proposal and what I've been investigating is the idea that cut integrals can be obtained. And so in this representation, you can't put p squared equal to 0 because you've integrated out p squared. You're left with some alphas. But I claim you can still find the on-shell conditions by changing this gamma, by changing the nature of the boundaries, by removing the boundaries for the propagators that you're cutting, and instead also including f equals 0 as a boundary. The justification for this idea comes from the Landau conditions. I wouldn't say this is quite proof yet, but actually you can make a cleaner argument based on discontinuities in different kinematic regions. So the idea is the Landau conditions are what led us to be looking at cuts in the first place. Landau basically wrote down two conditions for finding singularities. So if the inverse propagators are given by this capital AI, mass squared minus momentum squared for each propagator with an I epsilon prescription. These are the two Landau conditions. For each edge, the parameter times this inverse propagator has to be 0, and then there's something else for each loop. Now you can follow these conditions into parameter space. After you integrate out momentum, you can write them, and they were written in this form in the analytic S matrix book, that you have, f equals 0 becomes one of your conditions. Alpha, some set of alphas have to be 0. That sort of follows from this condition, right? Either the edge is on shell in the momentum sense, or the corresponding alpha equals 0. And then, depending on which alphas are 0, for the ones that are non-zero or not necessarily 0, you still have some conditions on the derivatives, which then turns into a condition on the derivative of f. So I'd like to interpret these Landau conditions now in terms of boundaries of the integration region in the spirit of expanding the space of functions. So we can draw some pictures. This is for the triangle integral, but now that's not this triangle. These are, the triangle integral has 3 edges. So I've taken, alpha 1 equals 0 is this hyperplane, alpha 2 equals 0, alpha 3 equals 0, the 3 hyperplanes, and then there's a projection. And this gives you, so this is the integration domain, the standard simplex for the original Feynman integral. And then for the other cuts, I identify some other regions which are bounded by f equals 0, which is a quadric, an ellipse or a hyperbola, usually for a one-loop integral. And then you just choose some subset, or you identify some subset of these bounding hyperplanes to give you the new integration contour. What can you do with this? Well, one thing you can do with this is you can identify linear relations. It's in more technical terms, a statement that's true in homology, but you can just draw it as an inclusion-exclusion argument on these regions in parameter space. And what this gives you is that the uncut integral can be expressed as a linear combination of the cut integrals, which is a relation we were familiar with, but has a pretty complicated derivation. And now in this picture, you can see it. You can see it very easily for any one-loop integral, just in terms of finding the regions. So you can select a basis of the function space, and I'm interested in pursuing this idea for more general integrals. So the vision, as coming back more generally, is that function space needs to be managed more generally. Maybe not everybody's working on Feynman integrals. We have amplitudes in different kinds of theories. I know you have functions in different kinds of theories. Sometimes we have some things in common. For amplitudes, I mentioned symbols have been very useful, but we're actually still at the point where we would like to. We know the symbols are there, we can do things with them, we can build unitarity methods, there are improvements in differential equations. There's still a lot of room for further improvements. Many of us are interested now, to what extent can we fully predict symbols of amplitudes? This idea is what goes now by the name of the symbol bootstrap. What exactly are the arguments of the logarithms, and in what order can they appear? More generally, we're looking ahead to elliptic polylogarithms, other families, iterated integrals more generally. I also know that in many contexts which are quite different from this, which maybe you encounter in your own areas, hypergeometric functions come up over and over, and there we have nothing like the symbol, nothing that gives you control over relations. There are many representations, we know there are many relations, and I would find it very useful, and maybe some of you would as well, if there were some theory, something even helpful like the symbol that would allow us to tame the complexity of relations among hypergeometric functions to help find a basis. So to close, I just want to say, control of polylogarithms has paid off richly. We built upon that a lot in the last decades for multi-loop amplitudes, Feynman integrals. Even in those cases, we do want better control of the symbols. Key concepts that we can take farther beyond polylogarithms are iterated integrals and these kind of periods, just constructing integrals for our functions by looking at contours and differential forms and how they work together. And just specifically, my idea that everyone is welcome to work on specifically as well, I can share some of the open questions, is to look at periods with parametric contours for Feynman integrals. Thank you.
Thank you very much for the nice talk. Questions?
For the second part of your talk, when you had this integral representation in terms of these Feynman parameters, those two functions which appeared inside this representation, those related to the semantic polynomial. Do you assume, for this construction, do you assume that one of these semantic polynomials is positive definite in the physical region of the moment or not?
That would be the starting point, but it doesn't have to be. Yeah, so...
the reason I'm asking...
Go
go on.
Yeah, so here... Okay, for example, what I've drawn here, this would be in what we call the Euclidean region. So there, a priori, you're integrating over that triangle in the middle. And the ellipse is, well, that's f equals 0, so f is positive inside and negative outside. But I guess what I didn't show here for lack of time is you can try to follow the shape of that curve into different kinematic regions. And you can see, well, in this case, you can see very explicitly how you pick up discontinuities. So actually, no, it's more the opposite. If you're looking for a cut, so here, let's just take this one, for example. So here's a region which I've identified as a cut of one propagator. But that's not really where it comes from. Where it comes from is I would start in the kinematic region where there's a discontinuity in that mass. And in that region, f equals 0 would slice through the triangle. And because I'm interested in picking up the discontinuity, I would actually be integrating over the part of the triangle where f is negative, because that's where the discontinuity is. And I'd set up an integral there. And then, really my claim is that I can analytically continue that integral now back into the Euclidean region and interpret it as this one here. I don't know if that was...
One of the reasons why I'm asking, because some time ago, when people are looking for the semantic polynomial, etc., they figure out there is yet another source of singularities, so-called global singularities. Those which comes from a certain situation when you have this function f, which is not positive definite in the physical region of the momenta.
Mm-hmm.
So my question was more like whether you cover these additional singularities, which are, they're kind of very special. They're not universal. It depends on which process you're talking about, but they appear in general from the contribution when f, this semantic polynomial, is not positive definite. There's some hyperspace in this parameter, Feynman parameter space, on which this polynomial could change sign.
Okay, well, I'd be interested to look at that further, but let me say again that since I'm always setting up a region that's bounded by f equals 0. So actually, when I said that I was integrating in the region where f is negative, then I actually integrate minus f to some power. I set up a well-defined integral there, but f is not changing sign because the f equals 0 is a boundary.
More questions? Well, if not, let's thank Ruth again.